Welcome everyone to our today's PCS IBS seminar. It is a great pleasure to have with us today Professor Yu Xiao-Quan from Graduate School of China Academy of Engineering Physics from Beijing. And our scientific host for today is Sergey, and he will introduce our speaker. Please, Sergey.
Yeah, thanks, Thielen, and welcome everyone. It's a pleasure to have Xiao-Quan Yu with us today for a PCS seminar. And let me say a few words about Xiao-Quan. He did his first he did his bachelor at the Department of Physics of Inner Mongolia University in China, and I was always wondering about what is then the Outer Mongolia. But we can discuss it maybe afterwards. This was just a little geographic joke. Then he moved on, now I'm serious again, then he moved on to the Capital Normal University in Beijing, where he did his master in mathematical physics. And then he moved to CISA in Trieste in Italy, where he did his PhD with Markus Müller, who basically CISA and ICTP are some kind of hard to distinguish things in Trieste if you have been there. So that's where Xiao-Quan did his PhD, which he finished in 2012. And after that, more or less after that, he moved to New Zealand and worked together with me at Massey University in Auckland until 2015. And then he moved on for another research fellow position at the University of Otago, which is again in New Zealand, but on the southern island, as opposed to the northern island, where he worked together with Ashton Bradley and Blair Blakey. And then he got a call and became an assistant professor at the Graduate School of China Academy of Engineering Physics in Beijing, he started this position in April 2019, and now comes the interesting part in his vita. He just started this position, and then he moved. He went back for a supposedly shorter visit to the University of Otago in Dunedin in New Zealand, and then COVID hit, and that is why he spent there a little bit more than originally expected. I guess probably of the order of 2 years. And only very recently he was able to return back to Beijing, from where he is now connected with us. And we look very much forward to your talk on Ferrodark solitons in a spin-1 Bose-Einstein condensate. Xiao-Quan, the floor is yours, please. Hello?
Hello, still connecting?
Did anyone hear me what I was saying?
Yes, we heard you, Sergey.
Good.
Yeah,
Good.
Professor
Yes.
Yu, we can hear you also now.
Yeah,
So
okay, good, thanks.
You can please start.
Yeah, the internet might not be so stable. Thanks a lot, Sergey, for the introduction, and also thanks for providing this opportunity for me to share some recent work with people in PCS, and I'm very happy to receive any feedback, questions, and then during the talk. And also, I would like to thank the staff members in PCS for helping me organizing this event. So today I'm going to present some recent work on solitons in spin-1 Bose-Einstein condensate. So why we want to do this? So a general question is that whether we can find stable solitons at high dimensions. Here, solitons, I mean particular topological solitons like the dark soliton and theta, not for the bright soliton. So normally, let's say in the scalar BEC, people know well that the dark soliton is unstable at high dimensions because the so-called snake instability. And therefore, studying high dimension dynamics of those topological defects are not basically possible, because before you're studying them, the soliton decays. So the question that whether in some other system, nonlinear system, such topological defects can exist. If yes, then we can open a door that we can study something very interesting, which in the past are not possible. So another motivation is more specific, which we want to ask what are the topological excitation associated with Z2 symmetry in the easy plane phase of a ferromagnetic spin-1 superfluid. So in the spin-1 BEC, people have studied quite extensively. In particular, these topological defects associated with continuous symmetry, like vortices, all sorts of different type of vortices. People know them very well. However, for those topological defects associated with Z2 symmetries, like kinks or domain walls, are less well understood. And those defects play a very important role in certain out of equilibrium process that's basically observed in the early experiment of the spin-1 BEC. However, the property of the defects are not very well understood. Now, why spin-1 BEC? Spin-1, to me, that spin-1 BEC is probably the minimum model to study magnetism in the background of a superfluid order. In a sense, you can study superfluid order and the magnetic order simultaneously. That's what this state exhibit. And of course, one can ask why not a spin-2 and high order. That's also, of course, possible. And however, that spin-1 BEC, probably that's the minimal model that people can work on. And then, so another motivation, I already mentioned that those defects, topological defects, like domain walls or the vortices, play a very important role in the phase transition, especially in 2 dimensions that we know very famous BKT transition. And that's driven by the vortices and also some out of equilibrium dynamics like phase ordering and dynamics and K-Bozoulik and etc. So that's all involve topological defects. Basically, studying the dynamics of the topological defects are the central point of those, or play a central role of those out of equilibrium process. And so that's why we want to understand better in this system that the spin-1 ferromagnetic superfluid, what's the role of the topological defects in the relevant process. And so this talk is basically based on this those recent publications. And yeah, let me go through the topic. And before going to spin-1 system, I would like to introduce some very basic notion or property, or introduce some basic property of solitons. I'm giving an example of scalar BEC, and the reason is that this solitons are called the dark soliton. Those properties are very general, does not only hold for scalar, but also hold for a large class of solitons. And I want to present some very basic property that's known very well. And then later, I want to show that what we find is very different from what we knew in the past. So here, the wave function is the exact solution of the scalar Gross-Pitaevsky equation that people refer this as gray soliton or dark soliton. The dark means that when the velocity here v is 0, it's dark because at the center of the soliton, the density go to 0. That's why called dark. When the velocity is finite, and then certainly at the core there is a density. And so one interesting property of this soliton is, if you look at the figure on the left, that's the density as a function of position and for different velocities. And we can see that for higher velocity, the density becomes shallower. And then at 0 velocity, of course, it goes to 0, but for higher velocity, it becomes shallower. And that's somehow consistent with the behavior of energy. If we look at the energy, the excited energy of the soliton on the function of velocity, it decreases, namely that for higher velocity, the energy becomes lower or smaller. And then if we expand this energy as a function of v at v equals 0, and up to a second order, we can see this term certainly we can associate with a particle kinetic energy. And the coefficient we can certainly interpret as an initial mass. And because the energy decreases as a function of velocity, the inertial mass is negative. So that's one fact that the inertial mass of dark soliton is negative. So what is the consequence?
Xiao-Quan, can you go back, please, one slide? So yes. Just for understanding again. So the soliton is a dark soliton here that is a dip in the density, right? A localized dip in the density.
Yes.
What do you call energy? Is that the energy difference?
The energy difference compared to the background density. Background energy, which is
okay. So you basically have a dip in the energy in the norm density. Sorry, but actually the energy is larger than right. So it's a kind of like an excitation, huh?
Exactly, the excitation energy. Okay. Exactly.
But what you now say is that this energy becomes smaller and smaller the faster the soliton moves. And at the same time, the dip becomes deeper and deeper. How do we understand? So that means basically that at the limiting velocity 1, you have some kind of degeneracy between this moving, this excitation and the, so to say, ground state you started from.
Exactly. Exactly.
Okay. Okay.
At the v equals to the largest velocity c, it basically becomes ground state.
So you have a kind of which means your ground state is actually degenerated.
Yes.
In the first place. Okay.
Exactly. Yeah.
Thank you.
Yeah. So, so what are the consequences of this? So the consequence is let me first introduce the so-called physical mass. That is somehow the trivial in a sense. Just count the missing particle number compared to the ground state. So basically just the nx minus n background density, and you take the integral and multiply the atomic mass. That's basically the called the physical mass. And apparently it's negative because we see that there is a density dip. Now, so okay, those are the two concepts why they are useful. Yes, it is useful because if we think a harmonic trapped BEC, and we imprint a soliton near the center of the trap, the soliton is going to do oscillation. And for small amplitude oscillation, this frequency precisely can be precisely expressed as the ratios of the two masses. And because they are all negative, certainly you get a meaningful number, and omega here is the harmonic trap frequency. And here I just show a movie, and so say what the soliton does in a harmonic trap. So just looks like a particle in a harmonic trap. However, the frequency, of course, is different from the single particle in a harmonic trap. Indeed, there's a famous square root of 2 difference between the two frequencies. But nevertheless, that we can say being a negative inertial mass, that's somehow explains this behavior, or at least we can think of it. It makes sense. Now, so what are the second consequence? That's the so-called snake instability. Here I present a graph from this publication, and they look at the quasi 2D system and imprint a soliton here, and look at the time evolution when there is a kind of transverse deformation of this soliton. And as a function of time, we can see that the deformation becomes bigger and bigger, and at a certain stage it breaks to vortex anti-vortex pairs, and the system is unstable. This is a so-called snake instability. So why so? Because we can imagine like a string and a straight string, and we can think there is a transverse deformation. And normally, because if there's deformation, there is a restoring force. So normally what happens is that just do oscillation. But here, because the inertial mass is negative, so the restoring force somehow making the deformation even larger. So that's make any transverse deformation larger and larger until reach the point the system cannot be stable anymore. It breaks to a more stable structure, which are the vortex anti-vortex pairs. So that's another consequence of inertial mass being negative, namely that this soliton has to suffer from snake instability. And now come to the point what Sergey already pointed out earlier, that what is happening at the maximum speed, which is speed of sound. So the question is that why there is a speed of sound? Why there is a speed limit of the soliton? Namely, the soliton looks like a nonlinear excitation. Why there is a speed limit of the soliton? And at least my understanding of this is that when you go to large C, and the wave function basically can be expressed as a constant density plus some perturbation. And of course, in this regime, we can think, oh, this is connected to the low-lying linear excitation, that's the Bogoliubov mode. And the Bogoliubov mode, of course, give us the speed of sound, because the sound wave that has a propagation speed, that's the speed of sound. And therefore, this soliton cannot propagate faster than speed of sound. So the reason is that it's connected to the fundamental velocity of the system, and then it cannot larger than this speed. So those are the basically three facts that people know very well. And later on, I want to say that the soliton we found is actually have very different from what I just said. Okay, let me give a very brief introduction of the spinner Bose-Einstein condensate. So this introduction is very brief. So if people want to know more, please go to certain review. Sorry, I didn't refer those references, but people can find references very easily. So what is the spin-1 BEC? So the spin-1 means that here is a hyperfine spin level, which is the total spin quantum number is 1, and there are three. Then there are three sublevels, and we can describe the state using a three-component wave function, and each component wave function describes the condensate of those three spin sublevels. And different from the Euro, say BEC or two-component BEC, where there is a density-density interaction. In the spin-1 BEC, there is an additional term. That term introduces a population transfer from zero component to plus minus component and vice versa. Not only population, but also phase coupling between the plus minus and zero components. So that introduce a very rich dynamics, and that term introduce magnetic order, and where that's why the system becomes more rich and interesting. So what I'm going to present is in the mean field level. So in the mean field level, people can arrive this Hamiltonian. The first term is the kinetic energy, as we are very familiar with, and the second term is the density dependent, or spin independent interaction, where that's only density interaction, and this term is a spin dependent interaction. Here S is SO3 spin matrices, and then here there's a Q. Q here refers to quadratic Zeeman energy, where mainly due to the magnetic field, and sometimes in the experiment that's also from the microwave electric field. But let's just think this is just the second order in magnetic field. So why we don't have first such magnetic field that's a linear Zeeman? Because yes, certainly it is there, but it's not important because the linear Zeeman basically play a role of shifting the plus and minus energy, and then in terms of spin language, that just basically produce the Lyman precession, and then that term one can make a gauge transformation and gauge that out, because that's not important for the physics we are going to present. And then as usual, one can certainly relate this density interaction parameter and the spin interaction parameter to two scattering lenses of the system. Because in the spin-1 system, one can think that the two spin-1 particle after scattering, the total spin can be 0 and 2, and then 1 is not possible by symmetry if we ask all these S wave scattering. And then there are two scattering lenses, and one can write those strengths as a related the strengths to the scattering lenses. So here a Q play a very important role, because if there is no magnetic field, the system process SO3 symmetry. Why? Because this spin dependent interaction. Because this is because S is there is a question.
Yes, Sung Jong, please unmute yourself.
Yes.
Yeah.
Maybe I can ask, since you already interrupted. Is total spin conserved by this Hamiltonian or not?
Yes, if Q is 0, the total spin is conserved.
But if Q is not 0, it still commutes with SZ, right?
Yes, exactly. The Q not 0, Fz is conserved, but Fperp is not conserved.
No, S square, is it conserved? S square is conserved quantity or not?
When Q equals 0,
No, Q is
F
not
itself
0.
is conserved. But when the Q not equal to 0, only Fz is conserved.
No,
but,
S square, it's not conserved. Total spin.
Sz square is conserved, yes.
I'm asking about S square vector, S square.
That is not conserved for when Q not equal to 0.
But I used to think that S square and SZ squared are commuting. So why it's not conserving? Okay, maybe.
Because the Q okay, I can answer from the symmetry point of view, because when there is a Q, the system only process SO2 symmetry. There is no SO3 symmetry anymore. So the total magnetization cannot be conserved.
Oh, I'm sorry, continue.
Yeah, yes. Okay, so there is another
please
question.
Continue.
Yeah, yes.
Yes, there's
okay.
another question. Sung Jong.
Yeah, I have a question about the Hamiltonian, the terms, the last two terms. Could you give any like short explanation in terms? I mean, I'm wondering what the origin of those two terms in terms of experiments. And I have one more question. So, yeah, so maybe the same. I mean, it's related question. So, the last term, is it like the expectation value of SZ squared? Is it the same with the expectation value of like square of like SC? No, I mean this is the last term is expectation value of SC squared, right? So is it the same with the square of the expectation value of SC?
Okay,
can I do the scale first? Okay, yeah.
Yeah, okay, good. Thanks for the question. Let me maybe first try to answer the first question, that where is the quadratic energy? So this normally I think quadratic term is harder to compute, but for the scattering, for the S-wave scattering, and there is a formula, I think it's called Barrett-Rabi formula, where that you can calculate you can calculate the moderate magnet when the magnetic field is not that big, not that small. One can get a very good formula for the splitting energy. And so why there should be a quadratic term? My understanding is that because here we are talking about a hyperfine structure, and hyperfine means that you need to consider the spin, the nuclear spin, and then the electron spin. And then if there is no magnetic field, there is already interaction between the nuclear spin and then orbital spin. And then if there is a magnetic field, the magnetic field will couple the total magnetic moment. And then these two matrices not necessary to be to commute. When you diagonalize this matrix, you can imagine that there will be a quadratic term in B. So that's the reason, I think. So in the experiment, so there is a expression for Q. I think this is, if I'm not very wrong, it's the energy. Let me think. The energy of plus of m equal to 1 component of energy of minus and minus 2 times energy E0. E0 is energy at m equals 0 component, and divided by the hyperfine energy difference without a magnetic field, and times B squared. So the second question, you ask the SZ square, whether that average equal to
so it's whether I mean the scale can be done first, or like I mean it doesn't matter.
Sorry?
I mean, so my question is whether the square can be done after you calculate the SC expectation value.
No.
So it's different.
It is not the FZ expectation value square.
Okay.
You can think this is the fluctuation of FZ.
Okay. So this is without external magnetic field, right? Without no external magnetic field. This formula.
No, Q. Yeah.
The Hamiltonian is
proportional
like,
to. Yeah.
Okay, okay.
Q is proportional to magnetic field square.
Okay, okay, I see. Okay, yeah, thank you.
Yeah. Cool. Thanks for the questions. And I think that some of the automatic physics I know very poor. So please, if an audience the people know better, please help me to answer those questions. And thanks a lot for the question. That's very helpful. And then in the experiment, certainly people can look at the there are physical realizations of those system. For example, for the ferromagnetic case, where the GS is smaller than 0, and there's rubidium and the lithium can realize this negative GS, and sodium has a positive GS, where that associated with anti-ferromagnetic. And come to this the system, we introduce other parameter, which is the magnetization. Basically the standard, the average of the this spin matrices, and in a different direction we can have a different component, and sometimes it's useful to introduce so-called F-perp, because if there is a magnetization on Z direction, and of course it's meaningful to define F-perp, which is perpendicular to the Z axis. And for the anti-ferromagnetic phase, that the system try to minimize the ground state, try to minimize the energy by vanishing the magnetization. With the magnetization 0, that gives the ground state. However, for the ferromagnetic phase, the system favor magnetized state, and then the magnetization is not 0. That's the phase we are focusing on. And depending on the quadratic Zeeman value, and then there is a certain parameter regime, which I showed here. In this regime, the system is in a state that the F-perp, the magnetization it's on the plane, and then Fz is 0. So this is not really precise, because Fz is conserved, so you can choose whatever value allowed. That's also possible, but here, because it's conserved quantity, we choose Fz is 0 here. And then that's called the easy plane, because the magnetic moment or magnetization is perpendicular to the magnetic field. And then, so this is the ground state wave function. So there are two parameters to describe this ground state. One is the global phase theta. So another is the rotation, SO2 rotation along Z axis. That basically this tau tells us the orientation of the transverse magnetization. Indeed, if we write down the expression of transverse magnetization, it is characterized by this tau. That's the angle of the magnetization on the plane. I think this is quite clear. And then so what are the defects? And because of, in our system we have two orders. So one is the superfluid order, so another is the magnetic order. And we can ask what are the defects associated to those two orders. So one is the defect means that Z2 defect is the so-called duck vector solitons. So what that means? It means that in each component we have duck solitons. We have duck soliton, and because apparently we can see from the previous slide that the wave function will change sign across the core, and that is certainly breaks the superfluid order, because and the wave function also changes sign across it. However, this vector soliton is not a defect in the magnetic order. It does introduce a hole in magnetization, but across the it is just a hole, but not the topological defect in a sense. The magnetization does not change sign across the core. So and then come to our focus, that is the Z2 defect in the magnetic order, which we name it Ferrodark solitons, and we will see why this name makes sense, why we call the Ferrodark. So, but what it is simply a transverse magnetic domain wall that connecting the opposite magnetized domain, magnetic domains. And so here, I mean, better to the picture, better to explain. And this is what we call the Ferrodark solitons. This is in 2D, and we can see the arrows present the magnetization, and the color presents the density. And one can see that the magnetization changes sign across the core, and also is 0 at the core, but the density does not go to 0. And that's exactly the defect, that this Ferrodark soliton is a defect in the magnetic order, but not in the superfluid order. In the sense that it's the superfluid density does not go to 0 anywhere. And then, so luckily enough, at a particular parameter regime, we find exact solutions of those solitons, or exact solitons. So they have two types, and so that is the magnetization, and have a typical profile of hyperbolic tangent, and that is the density somehow have a typical profile of hyperbolic second square. And the important thing is that regardless of velocity, at the core, the magnetization is always 0. So that's very different from dark soliton in the scalar case. Yeah? In scalar case, when the velocity is finite, at the core, the order parameter is no longer 0 anymore. But here, the order parameter is always 0 regardless of speed. And then density never go to 0. That does not depend on the velocity. And from this expression, one can say that, well, there's basically no difference between type 1 and type 2. The difference looks like only appear in the width of the soliton. And here is the expression of the width of the soliton. And later on, we will see the difference is actually essential, and we'll see later. But here, I just want to draw your attention on this Q factor. Apparently, this Q factor, the square of Q has to be positive by definition. And this requirement immediately gives a bound of the speed of the propagating speed of the soliton. And this bound is a new speed limit. So why is new? Namely, this speed does not agree. It's not given by any Bogoliubov mode in that system. So let's come to this plot. So this is in the easy plane phase. We look at the Bogoliubov excitations. We have 3 branches. So one is a gapped, and 2 gapless excitations. Those 2 gapless excitations correspond to one mainly spin waves, another mainly, probably mixed spin and density waves. And from these 2 gapless modes, one can read the 2, say, speed of sound, or yes, the two speeds. And then the speed we got is very different from this two Bogoliubov or the two sound wave. Moreover, interestingly, that for a particular in a particular parameter region, our new speed limit can be larger than the two speed of sound. So that's implying that there exists a propagating Ferrodarks with a speed greater than any speed of sound of the system, and looks like a supersonic, but actually does not introduce any noise or excitations, because as we just said that and at what in any speed the magnetization at the core is 0. Therefore, there's no magnetic current. So that's why that this speed is permitted. So then let us go back again this this bond. So what we can learn from this formula, we can say, when Q equals 0, this bond vanishes. So namely, this soliton cannot propagate. Yes, why? Because in the presence of magnetic field, the system process SO3 symmetry, the magnetization F is conserved. Therefore, imagine that we have a soliton or a domain wall, and then this is on the left, it's the magnetization on the left, and on the right, the magnetization in the opposite direction, and we can calculate the total magnetization, and that is fixed. So if the soliton moves, the magnetization will change. Of course, that's not possible because of conservation. So that's certainly is consistent. And so another observation is that when the velocity at the maximum velocity, the soliton does not vanish. Not like in a scalar case at the maximum speed, it vanishes. The nonlinear excitation becomes basically linear, approaching linear excitation. However, in this case, when the velocity at the maximum speed, the soliton still a nonlinear excitation, but the two types of the Ferrodark become identical because when this condition is satisfied, the Q value is 0, and then we get the two lengths are the same, and you can see that's the expression of the expression. The expression of the two become identical. And now we let me again look at closely the properties of those soliton. So here ABCD plots AC plots type 1 and type 2 Ferrodarks. Sorry, the F-perp of type 2 and type 1 and type 2 Ferrodarks, and it's at different velocities. It's hard to tell what's the difference, but if we look at on the right two figures, figure B and D, and we can find something interesting. Let's first look at the type 2 Ferrodarks. And here the solid line is for the maximum velocity, the maximum velocity, and the dashed line for small velocity. And yeah, that's expected because we can see as we learned from a scalar case, when the velocity increases, the density becomes shallower. Good, that's looks normal. And but when we look at B, that's a type 1 Ferrodark. Well, when the velocity increases, the density gets deeper. So that's exactly the opposite from what we see for what we learned from the scalar, and also opposite to type 2. And then so this behavior will be reflected more transparently if you look at the energy plot, which is the bottom plot. That is the excitation energy as a function of velocity. And we can see that the type 1 shows that the energy decreases as a function of velocity as in the scalar case. However, for the type 1, the velocity, the energy increases as a function of velocity. And then they match smoothly or connect smoothly at the maximum speed. And now, if we look at the energy curve of type 1, immediately remind us, oh, it means that the inertial mass of this type 1 Ferrodark would be positive. And yes, and certainly, and we can calculate at this exactly sober point, we can calculate the inertial mass. Indeed, exactly, and indeed, of course, it is positive. And I want to say that this is a purely nonlinear effect. As we can see that for density, we always have a dip. There is no hump or any. Of course, if some component has a hump and the system have a positive inertial mass, that could be expected. But in our case, all the component density has a dip, and then the inertial mass is positive. This is to me is quite interesting, and that's it's a nonlinear effect, not due to some positive hump in the density. And then of course, from this formula we can also see a consistent result, namely when Q equals 0, this inertial mass becomes divergent, become infinitely heavy, and then they cannot move. That's consistent with what we saw from other quantities. And for type 2, certainly the inertial mass is negative, and also at the Q equals 0, and it becomes infinitely heavy and it cannot move as well. And also in this Q equals to 0 limit, the two types becomes again identical. I will show later, but they identical through the SO3 spin rotation. Yeah, okay, now come to this question. Now we can ask ourselves that, okay, so if the system, I mean, we show that at the maximum speed, the soliton still have a good shape, it's still a nonlinear excitation. And somehow we can ask, what if we keep accelerating this soliton at the maximum speed? So what can happen?
Sorry, can I ask you one question? In your previous slide?
Yes.
Yeah, yes. Here, you discussed the initial mass around the Q equals 0, and you said that this is the nonlinear effect, and yes, I think I understand. But if Q is for example, larger than Gn times Nb, is it corresponding to some realistic situation where the parenthesis goes to the imaginary?
Yeah, a good question. Because we are, as earlier on, I mentioned that we are working on this phase called the easy plane phase. And then for this, for the ground state to be easy plane phase, Q has to be larger than 0, smaller than minus 2GSN. And then here, because this is exactly solver point, namely GS equal to minus GN divided by 2. Therefore, Q has to be smaller than this value because we start from this ground state. If Q larger than this value, the system will move to so-called polar state, where there is a only occupation EM equals 0 component, and that's another regime, and there's no magnetization anymore. So this excitation does not exist in that regime.
Okay, thank you. Thank you.
You're welcome. Yes, disturb me anytime. I'm very happy to receive any question that or any doubt or criticize anything. So yeah, come to this point that okay, so what already the maximum speed. What if we keep accelerating? So now comes to the phenomenon that oscillation in a linear potential. So in order to answer the question of what we asked, we consider a system, a trapped system, superimpose the linear potential. So be careful, just want to be very precise. This linear potential acting on any spin component, it's a spin independent component. It's like a harmonic trap. It's a linear, say, linear trap or linear potential. Of course, the system is trapped by the hardware potential, the whole system, and then superimposed by a linear potential. And this linear potential acting on every component equally. It's not acting only one or two components, acting on the every component. And then we imprint one type 1, say at the beginning, type 1 soliton at a certain position. So this is y-axis is the space, is one dimension, and then x-axis is the time. And the first figure shows the magnetization, and then the second figure shows the density, and third figure shows the velocity. And then what is happening is that when first at the beginning, the type 1 is going to accelerate, and when it reaches the maximum speed, because at that point, the type 1 identical to type 2, and it becomes a transfer to type 2. And because type 2 has a negative inertial mass, it starts to accelerate in the opposite direction, and then stop at another end, and keep moving in the opposite direction, and the same point in the change to type 1, and again once the transition happens, the inertial mass, the sign of the inertial mass changes sign as well, and then acceleration changes sign as well, and then later on retain the initial position, and then the process keep going without decaying. And during this motion, that the magnetization always 0, and then for density has also very mild change. And if we look at the measure the velocity of this numerical experiment, we can see that velocity reach the maximum velocity, and then and change the type, and then one can see the this process as what I just described. And of course, this certainly reminds us a very famous phenomenon called the Bloch oscillation, which my understanding of Bloch oscillation is that you need a periodic structure, you need the lattice, and superpose a constant field, electric field, and we can see that in the presence of a linear potential and say oscillation. And here, however, we do not have a built-in periodicity, so that's but we see this oscillation in a linear potential. So I think that's we could somehow say it is as a interaction-driven Bloch-like oscillation without built-in periodicity. And so that's another plot to see the same phenomenon. And just in this case, we say in more details that in each component, what are the changes. And then we can see again that if we initially the type 1 and at the maximum speed and they become identical, and then later become type 2, and then this process continues. And if we measure the excitation energy, and then we can map this excitation energy to a uniform case and compare to the analytic curve, and we can see that indeed the energy basically follows this loop from type 1 and type 2 and type 1 type 2. And yes, here I just show a movie that might be more transparent. And before I go forward, go ahead. I just want to see that this is the plus or minus component on the left, and the right is the 0 component, and this figure is for total density, and the last figure on the right bottom is for the total magnetization. Yeah, that's basically very stable dynamics, and it just keep going and forward and backward. So I probably can stop here. Is there any question at this point?
Sorry, can I ask you one question?
Yes.
Is the two types, type 1 and type 2 excitations, are they related with the SU2 symmetry of the system?
Good question. That when Q not equals 0 in a finite Q, the system only process SO2 symmetry, and then there's no way to bring type 1 to type 2 because there is even an energy gap. You cannot rotate. And however, at Q equals 0, one can rotate type 1 to type 2. They are basically equivalent. I will show this later.
Okay, thank you.
Cool, thank you. Okay, so let's just briefly talk about the mechanism of the motion. Because this magnetization is always 0 at the core, therefore, if we write down the continuity equation of magnetization, and because the GF is the magnetic current is always 0, therefore the motion, the change of the magnetization is basically driven by this kappa. What is kappa? Well, the kappa is a quantity related to the nematic tensor of the system. And nematic tensor, we can understand that it's basically a higher order momentum of the system. This is something quite interesting in the sense that the motion of the first moment is driven by the second moment. And then this kappa proportional to Q, and of course, again, the same story when Q is 0, and there's no propagation, and the Ferrodark must stay still. And then one thing I want to say here, this is very general. I want to point out, just want to show that how interesting of the system is that one can actually write down the continuity equation of each component densities. And then if we, and then this continuity equation has a particular part, which is this internal spin current. So what is the spin? Sorry, this is not this one. This is just the traditional current in each component. This the red part is the spin current. So the spin current is nothing but tells us the two m2 particle can go to plus and minus and vice versa. So that's just reflect what we just said at the very beginning. And if one can write down this this current in terms of phase, and then one can immediately recognize, oh, this is quite similar to the Josephson current. I think that, however, of course, the Josephson effect is the linear effect, linear coupling, but here the nonlinear system without this coherent coupling can also generate this Josephson-like current. Here I just want to show that the wave function. I only showed the order parameter, and I didn't say the precise wave function. And here is just the table shows the exact solution. And then the current, of course, is localized at the core as expected. I just quickly go over that. Now come to the point and also the question as what is happening at the Q equals 0. So at the Q equals 0, because the system has now SO3 symmetry, one can do a spin rotation, and then depending on the angles you choose, one can rotate those Ferrodarks to many different other excitations. So here we list two typical excitation that are known in other community. One is the so-called, of course, again, in this case, type 1, type 2, they are equivalent just by particular spin rotation. Moreover, one can rotate to another soliton, and that soliton is actually a sine-Gordon type of soliton. So depending on how you rotate it, this nonlinear excitation has a different representation. See? And by another rotation, one can relate this excitation to a density domain wall, like in a immiscible binary BEC. Funny enough that somehow by this spin rotation, one can relate it to miscible binary BEC and immiscible binary BEC. They are unified through this spin rotation. This is quite funny. The reason for that is that normally, of course, a linear combination, any transformation, of course, just a linear combination of the different components. The linear combination of nonlinear solution normally not a nonlinear solution anymore. However, if the linear combination respect the symmetry, which is here is the SO3 symmetry, such rotation is permitted, and this linear combination can be another solution. So that's what I want to say. At the very end, I want to show that, okay, we were saying, oh, high dimension dynamics, what they are. And here I just show one example at the Q equals 0 case. Here we prepare a 2D quasi 2D system trapped by a hard wall, and we prepare a line type of excitation, line type of Ferrodark, and we deform it, and it just do a kind of harmonic oscillation. And we can also think we make it in a loop, and then they also show basically a harmonic oscillation of the string of the closed Ferrodarks. In order to show that those oscillation of course stable, we can also add certain white noises and white noise, and indeed that the motion certainly being deformed, but the whole excitation are still there. Okay, those bring me to the end of the talk. So I think we find somehow in general sense, we found a soliton with a negative physical mass, however, a positive inertial mass. So that's very unusual, and that implies that in 2D it will be stable and it will not suffer from snake instability. But I didn't present that, but that's indeed the case. And also those properties I just presented in the exact Sobob case hold in whole easy plane phase. So of course, away from the exactly solvable point, we don't know particular formula, but the properties, although the properties still hold. And also would like to mention that a recent experiment indeed in Korea, in the lithium spin-1 BEC, that they prepare the system near the exactly solvable point, which I think is very, very interesting direction. Well, there are some ongoing projects that we would like to understand better the dynamics of the solitons and how those solitons connect to spin vortices, and what those solitons Ferrodarks play a role in the equilibrium or out of equilibrium dynamics. That's the future project we want to explore. At the very end, I want to show a movie, just try to say that once we open the high dimension dynamics, there are many things could do, and I just show you one movie. I just prepare the two Ferrodarks in this 2D system and let them interact or collide. Sorry, let them collide. And in the past, we see many experiment or numerical experiment or study of soliton scattering on 1D, but in 2D that's very rare. And then so let's see what we will see. So they form a bubble, and then they keep going. And if I they can hit the boundary and coming back, and etc. So okay, that I think that's bring me to the end of the talk. Thank you.
Thank you, Professor Yu, for this interesting seminar. Let us thank our speaker.
Thank you.
And we have time for questions. Perhaps let me start. So this, the last video that you've shown, so this is then calculated in continuum, or is there this on a lattice?
In the continuum, not on the lattice.
Mm-hmm. Mm-hmm. Do you expect on the lattice to have different behavior?
Well, in the lattice, the periodic potential may play a certain role, and then if I think that if the excitation energy is not larger than the bandwidth, will be similar. But if the excitation larger than bandwidth, one probably can see some magnetic breather or this self-trapping effect. And then I think things will be different there.
Mm-hmm. Is this also part of your interest to consider lattice, or you focus on continuum?
Indeed, that's a good question. I thought about this system in a 1D lattice. Basically, I thought something similar to what I did in the past with Sergey in the disorder case, to look at the magnetic wave packet spreading, say whether the disorder in in a density or in a magnetic order, they may it may introduce different spreading behavior. And another thing, of course, that in this lattice system, there is interesting statistical mechanics, those this non-Gibbs phase and theta. And in the spin-1 system, I don't think that has been somehow explored for those non-Gibbs state. But that may or may not relate to the Ferrodark's talk here. But in general, I think that yeah, I thought about that and I proposed this to a student, and the student didn't want to do it.
Okay, perhaps more luck with another student. Thank you for the answers. Do we have any other questions from the audience? It seems not. So in this case, let us thank Professor Yu again.
Thank you.
And with this, we conclude our today's PCS IBS seminar. Thank you all for joining.